And we are live. Hello, everyone. Welcome to AST 111 in the spring of 2019. This is the Earned Admission program. My name is Frank.
I'm Becky.
And we are the teaching staff for the course. We're the ones active on the discussion boards, sending emails. So for this YouTube live session, we're going to talk a little bit about what we do. And then we'll answer some discussions on some questions on the discussion board, and then time permitting, we'll do a little presentation or so on stuff. So, Becky, what do you like to do for research?
Okay, I am a graduate student at Arizona State, hopefully my last year, and I do research on extrasolar planets, planets that go around other stars. In particular, I study planets that, when they're going around their stars, they transit between the star and us. So it's kind of like an eclipse, you know, if you're watching the star and the planet passes between its own star and us, then it's going to block a little bit of the light. So we just study the variations in the light and what kind of light signatures we're getting from that in order to learn more about the planet and its atmosphere and things like that.
So are you more in the exoplanet hunting game, or are you more in the characterizing the ones we know?
We're more in the characterizing of it and the instrumentation side of that. So instrumentation being, I'm working on the cameras and systems we would use to do our research. A lot more stuff like building things and testing cameras and stuff like that. And our cameras actually only can look at like one target at a time. So we're looking at targets that have already been found and studying them to find out more about them.
You put that light through a spectrum?
No, actually, we're working on near infrared detection specifically, and so with our camera, we haven't worked out the filters yet. But when we're using other infrared cameras, we're actually just using filtered. So it'll look at wavelengths, like specific wavelengths of light, and looking to see what kind of detections they make that way, rather than a spectrometer.
Got it. So it's broadband.
Yeah.
What have you found so far?
We've mostly been, because we're testing our theories, we've mostly been confirming different stuff that's already been detected. Near infrared is useful because there's certain molecular gases we can look for in atmospheres that we hope would, from everything we've studied, believe is linked to potentially seeing life. Of course, you know, there's always a possibility there's a reason for something that we don't know of, so maybe it's not an indicator of life. So there's also, you have to sort of take everything with a grain of salt. But we're mostly just looking at planets that already have a good amount of characterization done to see if that our systems can't match the information that they have already found.
Cool. What's some of the advantages of your system as opposed to others?
The cameras that we're working on, basically, when you look at the near infrared for astronomy, we generally use these cameras that are developed specifically for infrared astronomy, and they're extraordinarily expensive. And so we're actually using some cameras that were made commercially, and we're proving that they can, in fact, do the information that we want. They can do the observations we want, because they are literally 100 times cheaper, and so you could get a bunch of them and put them on a bunch of small satellites instead of getting like 2 and putting them on really big telescopes.
Right.
Sorry, not small telescopes, small telescopes. So it would bring down the cost of doing surveys in that bandwidth by a lot.
Cool. Aliens for cheap.
Yes. Hey, I mean, people underestimate how important that is.
Oh, yeah. Sure. Factors of 100 in cost are pretty big.
Yeah.
Cool.
So, and the big thing is just being able to, deploy arrays of telescopes with these cameras on it would open up a lot of different opportunities and reduce a lot of certain types of noise.
So these go on terrestrial scopes, or these go on like CubeSats or something like that?
Terrestrial.
Terrestrial. Okay.
So.
Ground based.
Yep.
Yeah. Cool. Very cool. I look forward to reading your thesis.
When there's something written to read,
you'll pass it along, I'm sure,
yeah.
to the appropriate. Okay, so what do I do? That's a good question. I do stars, generally, broadly defined. Excuse me. I like stars of any shape, fashion, or form. I'm particularly fond of ones that go boom in the dark night sky. So novae, gamma ray burst, X-ray burst, novae, things along those lines. And not just for the light show that they make, but it's from the stars that the periodic table of the elements come from. So it's stars that make the elements, which then make you and me. So I find that organic connection between the cosmos and us to be fascinating. And so a fair bit of my research is involved in creating the elements and the stars that make those elements is broadly what I do. Yeah, you can ask me a question about that if you want.
You gave it pretty broad.
And I do other things as well for the community, astronomy community and elsewise. So.
I'm not even sure what to ask you about stars.
You'll think about one. Okay, why don't we go ahead and transition into answering some of the questions that came up on the discussion board. Let's see, what do we got? Let's see. Number of questions on doing lab problems on these YouTube live sessions. We're not really set up for that, to do that effectively. And I'd rather do that on the discussion boards anyway, where I can be a bit more detailed and expand a bit if necessary. So yeah, we're gonna punt on doing those and put those on the discussion boards, which you should feel free to ask questions about. Happy to expand upon those. You'll find several examples already of me working things out, going through. Here's one we can riff on. This is from H. Castle 1, if I said that right. Thoughts on the future of space exploration? How close are we to getting a human on another planet? Is terraforming too far off? Things of that nature. So yeah, let's talk about that a little bit, Becky. Let's see. Let's see. Current stuff that's up, particularly with regard to planets. So one telescope that is at its end of life was a Kepler telescope, and the primary purpose of, and then its follow-on is called the TESS, the Terrestrial Planet Explorer, something along those lines. And the primary function of Kepler and TESS is to find Earth 2.0. I mean, that's the gold at the end of the rainbow. And so the way they search for that is through transits. So as Becky was just talking about, when a planet transits in front of its star, it makes the star get a little tiny bit dimmer.
He's transiting extrasolar space survey, extrasolar planet space survey.
Thank you. That's TESS. And it's a very productive method. I would say at this point, most exosolar planets are discovered by the transit method. And you can tell all kinds of things about them. So that's two of the current ones, one at its end of life, one just starting up. They're just starting to get their first observations up. We've got stuff going on in our solar system. We've got probably a mission to Enceladus coming up. Probably going to drill through the ice. and take a look what's under the ice, looking for life beyond Earth. And that's some of the astronomy stuff. Do you want to say about, you want to pick that up?
When it comes to specifically, I don't know, like the space exploration, I think in the question they're talking about people on other planets, even on planets within our own solar system. There's some things that have to be gotten over when it comes to moving people within our own solar system. But despite what the movies say, there's not very many good ways that we've come up with to prevent radiation from the sun from causing a lot of damage while people are on spacecraft. In fact, like, we're just sort of gambling that there's not going to be something bad that happens while people are in space at the moment. And going to the moon, which is only a few days, that's not so bad, but sending people to Mars, they're going to get hit by some pretty nasty radiation by the time they get there. And while they're there, there's not much in the way of shielding. There are astronauts. What?
Yeah, we will actually cover that in this course a little bit later when we get to the terrestrial planets. Mars does not have much of a magnetic field, and therefore the solar radiation and particles just come booming down onto the surface.
And there's actually quite a few technologies, like we might be able to send somebody to Mars, but we wouldn't be able to keep them there. We're not even close to terraforming, but even just if you ever saw the movie Martian, where he has like Matt Damon's trying to stay alive on Mars, a bunch of the systems they talk about that keep him alive, we don't actually have yet.
I liked all the potatoes. The potatoes were great.
Yeah. Personally, I think the book was a little bit more in-depth and realistic and a lot funnier. But it doesn't change the fact that a lot of the stuff that they saw in that movie that were supposed to be, you know, good things, like things that we don't actually have to keep people alive. Like, we wouldn't be able to keep a steady flow of oxygen right now. At least not continuously. The best we could do is kind of what they do in the book, which is create a bunch of oxygen, filter, and hopefully they don't keep them there long enough for there to be a problem. But long term, it wouldn't work.
I like that word, hope.
Hope. Well, I mean, in that movie, that was kind of the whole thing ran on hope. Hopefully this will work, but
hope. Although I do find it pretty interesting that generally our art sort of leads us where we want to go, and we try and get there, whether that's a Star Trek or The Martian or any of that. It gives us visions to go for. And part of that question was terraforming. Terraforming is remaking the surface of a planet, presumably in less than a human lifetime, because we don't want to wait billions of years to do terraforming. Terraforming also operates on energy scales that we don't even touch right now. That's just energy usage beyond what we can do right now. It's a great goal. Maybe it will happen, maybe it won't. But we're not there yet. We don't command that scale of energy on time scales that we got. But yeah, if you could, yeah, of course, there's lots of science fiction and movies on, you know, turning Mars into Earth, particularly as the sun ages and the sun begins to swell and turn into a red giant. Eventually, the inner planets go inside the sun, and so the idea is that Mars would sort of be the next balmy place to live when that happens.
Except that wouldn't work.
Yeah. So maybe by that time we'll be controlling energy at that scale. We shall see. Or maybe just nature will do it anyway because the Martian surface is heating up. Still doesn't have a magnetic field, though. That's an issue.
The magnetic field's the bigger problem.
Yeah, that's a huge issue. So as we'll see in about 2 weeks in this course, the magnetic field is super important because it basically acts like a cocoon. And so Earth is in a cocoon, and it shields away most of that dangerous radiation and particles coming in that can have great biological effects. And so we get shielded by our very comfy active magnetic field. Mars, being smaller, lost its heat, and therefore it lost its ability to generate an internal magnetic field. And therefore all that solar radiation and all those particles, cosmic rays, come booming down on the surface, which is generally not so good for biological entities. So yeah, that is a problem.
Yeah.
And I don't know, I haven't heard of any science fiction where somehow we inject heat into the core and remelt the core and make it generate a magnetic field. Wow,
that'd be so much heat.
That would be energy scales. Wow. Yeah. Okay. Let's see another lab question. More lab questions. Can we talk about what gravity is more physically and how it differs from other fundamental forces such as electromagnetism? Maybe get into a discussion of dark energy. Okay. Well, as we're learning in this week in the course, Newton's gravity law, that the force of gravity between two objects is a constant called G times the product of the masses, M1, M2, all divided by their distance squared. So G M1, M2 over R squared. So this describes how gravity, a two-body gravity works. But it doesn't say what it is. It just tells you how it works. And Newton, when people asked him, but what is gravity? He famously replied, I frame no hypothesis, meaning I don't know. This is how it works. We can do all kinds of cool stuff with it, but I don't know what gravity is. And so that took a couple hundred years till we got a better picture of what gravity is, and that's what Einstein gave us, one of the things Einstein gave us. And so gravity is actually physically, it's the curvature of space. And so that rubber sheet analogy is common. It's flawed in a couple of ways, but it's a useful picture. Where you take a sheet of rubber and you pull it down in the middle and you put your ball in and it spins around on that depressed sheet. And it's that spinning around on the sheet it's that curvature of the sheet that is gravity. So gravity is the curvature of space. That's the physical picture. And that has passed all known tests of what it is. So gravity is a manifestation of curvature in space. And that's pretty cool. I don't know. You want to say anything on what's the difference between gravity and photons, electromagnetic forces?
I don't know. Gravity has actually can affect the electromagnetic forces. Like light, it's one of the first things that they could test about Einstein's theories was that light that passes close to high gravitational area, say what they tried to do was measure the bending of light of a star that was very close. From our point of view, the light was passing very close to the sun, and so the light that was passing the sun would actually bend a little bit as it moved around, which it does do. We just proved that the experiment that they tried was wrong. It just didn't quite match up with what we were capable of doing at the time. But
now we are.
Yes, now we can do it. Especially because we can do that kind of observation around heavier gravitational bodies than our own sun. Like when we see light passing through areas that, we have, when we look way up, that is supposed to be off. Sorry, I thought that was on silent. when we look out into the outer space and we look at galaxies, if we look at galaxy clusters, we can see light arcing around from behind the galaxy clusters, because like galaxies that are behind them, as the light tries to pass around, you'll see like arcs of light being bent around the galaxy clusters, because the galaxy clusters have so much mass. So gravity is not affected by the light the way light is affected by gravity, I guess, as far as anyone has been able to tell.
Right. So one commonality they share is that they both, the force that they impart, both scale as 1/r². So the force of two electrostatic charges, for example, instead of m1, m2, it's the charge on one times the charge on the other, divided by their distance squared. So they are both long-range forces. They're the two long-range forces in the universe. So gravity and light operate on large scales, so the universe. All the other forces are short-range scales. So these are short-range scales associated with atoms and nuclei. And these operate, of course, on very short distances, because atoms are small, nuclei are small. So it is curious that the two long-range forces have very similar forms of a product of their main feature divided by their distance squared. Okay, dark stuff. Let's say about that.
We don't know much about it.
We don't know. Not a lot you can say there. The way people infer that there is dark matter, and let's make sure it was actually dark matter, right? Dark energy, that's different. Okay, so there's lots of dark stuff. So dark is just a general term for our ignorance, meaning we don't know. So we call it dark. It also means that the material does not generate light or doesn't interact electromagnetically. And so evidence for dark matter is fairly firm. And you can basically look at how bodies orbit other orbits. And if there was not additional mass there, the body would go flying off, a la Newton, like we're studying this week. And so the inference is that there must be mass there that we're not seeing, hence dark matter. Dark energy is a little bit different. Dark energy we infer from taking a look at how the universe is expanding, or now that we know it's actually not just coasting along expanding, it's actually accelerating. It's the accelerating universe. So the universe is expanding faster and faster as time goes on. And the root cause of that is what we call dark energy. What is causing that acceleration of the expansion? And we don't know what it is. People are looking. There are terrestrial experiments aimed at trying to, if it's particle based, people are looking for particle solutions, both the dark matter and dark energy. And then there are more cosmological probes that people look at to try and discern what is the, at least the behavior of the dark energy, or, as opposed to what is it? Okay, how does it behave? What effects does it have? So it's a frontier. We don't know, but people are looking. That makes it exciting.
Yeah.
It's always the things you don't know that, or don't fit the standard paradigm, or don't fit the model, that are the outliers. These are the interesting cases that lead you to new insights, to new laws about nature. What else we got?
Love when you try to go pick on something and you accidentally close it. Trying to remember. there weren't a whole bunch of other questions.
One's down toward the end. We've got M. Hedberg.
I've never heard of anybody thinking about.
Well, just go ahead and read the question. So.
It was. We've put. It's about how we deal with nuclear waste. And where it's stored so far. This one is we have put nuclear waste. The question says that we've been putting it in the oceans and near the Antarctic, but we haven't been putting it in those places. We've been putting them under mountains mostly.
Yeah, mostly under mountains, under relatively stable geological stratifications. People have talked about, particularly in the 70s, people talked about putting nuclear fissile material in Antarctica. That turns out to be a really bad idea for several reasons. First of all, it's not very stable geologically. And second of all, it's obscenely expensive to transport nuclear products. You've got all kinds of safety and security while it's in transport. You have to build the infrastructure to put it down deep. Some people have talked about it, but we don't actually store nuclear fissile material in the Antarctic.
It's much cheaper to put it in rock than ice.
Absolutely. Plus, yeah, you have to transport, and it's just crazy. So yeah, that's not done. Plus, and then in like the late 1950s, there were various treaties that were signed, making it illegal actually to do nuclear testing or store fissile material in the Antarctic. So I'm not sure where that information came from, but
the only kind of thing, like we've never put nuclear waste in the oceans. The only thing they've ever done is test nuclear weapons in the oceans, because as the radiation filters through the water, it makes so it doesn't go up to the atmosphere. But we've never stored anything under there, because if the waste broke open, it would move through the ocean currents, and that would be very bad. We always do it on land.
Yeah, plus the pressures at the bottom of the ocean, I think, would be pretty high. Putting a great stress on whatever your container is. So the chance of leakage goes up. And ditto for putting it on the moon. I mean, moving nuclear fissile material is very expensive propositions. And blasting it up to the moon is even more problematic. In fact, for long-term missions, space missions, people will use small nuclear fissile material to generate electricity, to generate power. And even that causes a great deal of cost and association with it. And in fact, for a while, there was a movement away from using nuclear power for spacecraft, precisely because of the safety concerns, right? What if you launch this thing and it blows up, and now you've got a small bit of radioactivity going all over the place, which freaks people out. So we try not to do that anymore. So I think sending nuclear waste to the moon is probably not very feasible from a safety perspective, from a cost perspective, from an international perspective. So
I think probably the best way to deal with nuclear material is that there are, in fact, ways, not all countries do it, but there are ways to recycle.
Right.
You like repurify material, you use it over and over again, and so you'll end up with a smaller volume left over overall, and you'll be able to use the material more times. There's just people worry about repurifying nuclear material, and like the United States is always worried about terrorism things.
Right.
I don't think that's the real problem. I think it's just they don't want to deal with the infrastructure, but they get upset, and so they try telling us that it's for our own good.
Yeah, the infrastructure needed to recycle is not light. Let's put it that way. Yeah.
That's the real reason they don't want to do it, is because they don't want to build the infrastructure.
Very okay, question 2. It is well known that the moon influences vegetation growth, and that the gravity force of the moon has certain effects on the tides we have on Earth. It would be interesting to hear my perspective or our perspective on the matter. Tides. We're covering tides this week in this course. Where tides come from, and the effects they have on the water bodies on Earth. This is what gives rise to the tides on Earth. So yeah, we definitely cover that this week, right? And so tides are basically because bodies are finite size, and for example, the Earth pulls on your toes more than it pulls on your head, and that causes a small tidal force across your body. It's very small, so you don't feel it, but on things of much larger scales, like planets, that tidal being closer to the source of gravity and farther to the source of gravity will drive the tides that we have. So yeah, it's a great topic for this week. I don't know about, I'm unaware, let's put it that way, of the moon influencing vegetation growth, at least gravitationally. I know there are some flowers that will flower at full moons at particular times, because they're picking up the electromagnetic signal, but I'm not sure about gravity.
There doesn't seem to be, there's like a lot of theories, but there doesn't seem to be a lot of consensus. I was looking at that when I saw that question. There are a lot of people who have, there's not just theories, there's a lot of like discussion about it, but people seem to disagree as to how much it really affects things.
Well, we certainly have done experiments in the past, like on Space Lab at our International Space Station. People will grow, let's go back to potatoes, since we brought potatoes into this. People do growths of plants in low gravity environments, right? It's not that there's no gravity up at the space station. There's plenty of gravity. That's why it goes around. So lower gravity. And so people are studying the effects of plant growth, plant flowering, plant reproduction, etc. But I'm unaware of any firm claims that, I mean, I will generally believe in broad terms that the amount of gravity affects how terrestrial plants will grow. I'll buy that. But I'm unaware of any specifics on specific plans.
Yeah, there may be effects, but they're going to be overtaken by the effects of things like weather, climate, local factory activity, pollution. Are going to have a much stronger effect than the moon will. The moon might have an effect, but the other things will overshadow that.
Okay, then we have the third one. Oh, yeah, actually, your question sparked me on this. So it is believed that the ancient Sumerians knew something about the planets. That part's true. They actually had a fairly sophisticated observing program of those only 7 dots that moved in the night sky, otherwise known as the planets, which then they passed on to the Babylonians, which then they passed that on to the Egyptians, and on it went. And then we have something about a certain cylindrical seal depicting 12 objects, some planet with some name, and then some character discussing that seal in a book on the 12 planets. So I did briefly look into this. I'll just be blunt. It's crank. It's nonsense. What is being proposed? So this particular author believes that the ancient Sumerians were visited by extraterrestrials from a 12th planet orbiting orbiting Earth. And so that's how they got their astronomy knowledge. And obviously you're visited by extraterrestrials, you get a lot more out of the deal than just that. But that's all silliness. There's no evidence whatsoever for a 12th planet. There's no evidence of anybody ever being visited by an extraterrestrial. And the particular cylindrical object that is being discussed, if you actually do the translation of the Sumerian or the Babylonian, it doesn't have anything to do with planets. It's talking about a local ruler. So one is free to believe whatever one likes. But as far as the astronomy goes, as far as the science goes, this one's not so good. Let's put it that way. I'm going to leave that alone. Okay, but thank you for asking the question.
There was a question that got posted a little bit after that about events and such in Arizona for observation.
Oh, yeah.
In May. I'm not finding any particular events, but there's quite a few clubs, and I know that there's definitely an astronomy club here. So there's definitely places to go, but there's no specific events, I think, in May.
That's something we can look up. We can post on the discussion boards of stuff that's up in the night skies for the month of March and April. Might be coming out. There's like 4 or 5 astronomy clubs in Phoenix, and there's probably just as many as that in Tucson. So yeah, that's actually a good idea. We'll look up like cool stuff and get it posted. And I've got some action going on not too far from my room. Sorry for the cross noise here. Oh boy. All right. Yeah, that's a good idea. Okay, so what we got? We got 10:38, so we have maybe 20 minutes left. What I could do is start a little presentation about time. So why don't I do that to get some time rolling, and then we'll keep looking for questions. So if you got stuff, go ahead and post it, and we'll take a look at it. In the meantime, I will cover something a little bit about time here. So I'm going to do a screen share. Screen share. Let's see. I guess I want to share this one. Start screen share. Can you see that, Becky? I saw a nod, so I'll take that.
Yeah, I put it on mute so that I don't pull your screen share down every time I make noise.
Oh, right, because the focus is on the noise. Okay, so the passions of astronomy are no less profound because they are not noisy. And this is from the only political satire that John Steinbeck wrote. This is in the short reign of Pippin IV. And as it turned out, this commoner who's was fond of riding his motorbike, as shown in the cover image there. He was an amateur observational astronomer. It turned out through some craziness that he had some distant bloodline to King Charlemagne. And the political powers that be decided they needed him to be king, or the president of France. And so he was brought up and installed as the president of France. And he really didn't like that, mainly because he couldn't get out and do his beloved astronomy, his passion for astronomy. And of course, the political winds changed over the course of a few weeks, and then he was kicked out as king, or kicked out as president of France, so he could go back to his astronomy. But it's a short read. It's a great little read. It's the only political satires Steinbeck did, so go ahead and give it a read if you like. Let's see. What I want to do is I want to go on single page. There we go. Okay, so we're going to talk a little bit about time, where time comes from, how how we keep track of it and why it's divided in certain ways. It's just a little piece of artwork here on a 24-hour clock in the Big Dipper. So 'tis the season. And when you have an agricultural dependence, you need to know when to plant and when to expect the first frost and when to harvest. And that's fine. All you've got to basically do is go by the sun. Do whatever the sun is telling you. You have to keep track of the seasons. That's why we have Stonehenge and other devices to be able to tell the time according to the sun. But as societies grow more complex, they end up wanting to have fixed dates for things like festivals, the 4th of July, or your birthday, or when to pay your taxes. And they want these to be fixed dates in the calendars. And this immediately introduces the difficulty of keeping the seasonal calendar, which is the time that the sun says it is, and your imposed calendar. So we'll have the seasonal and the calendar year. So the calendar year is the man-made imposed calendar. I want fixed dates for this, that, and the other thing. And the seasonal calendar is what the sun says. And you have to keep those synchronized, because if you don't keep them synchronized, if you go with your man-made calendar, then after a while, soon you will be celebrating summer when the sun says it's winter. And so you've got this clock synchronization problem that you have to deal with. And a lovely shot of the 4th of July in Tempe, Arizona. So it's a year. Just for reference as we go along, the seasonal year, that's the time defined by the sun, is defined as the fall equinox to the fall equinox, or excuse me, spring equinox, vernal. And it's about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. That's the year to 6 significant figures there. And then keeping track of clocks is what this is all about, and hence the persistence of memory from Dolly on the image. So yearly calendars, when they were started out, were first based on summer solstice to summer solstice. That's fairly easy to track, or when a particular star first rose with the sun, and this is known as a heliacal rising. And so the Egyptians used Sirius, which is the brightest star in the night sky, and it rose with the sun in early July when the Nile River was in flood. And with an economy based on the Nile floods, the heliacal rising of Sirius was the most important, and hence the first day of the Egyptian year. So it's like their January 1. So their January 1 occurred in this image. It's shown here. This is in 2000 BC on July 15th at 5:40 a.m. in the morning. And there's the sun on the left, and you can see Canis Major, Sirius rising with the sun in mid-July. And so this would be the equivalent of their January 1st at that time. And it was also a very easy timekeeper. When does this particular star rise with the sun? And that's how we keep our time, and that's how we go from year to year. So Sirius is the brightest star in the constellation Canis Major, sometimes called the dog star as a result, but it's from the Egyptians. Use of the heliacal rising of Sirius in early July. It's where we get the phrase, the dog days of summer. So we're going to see as we go through here that a lot of the mechanisms that were put in place by the Sumerians, by the Babylonians, by the Egyptians, by the Romans are still with us today. So this bit of time in astronomy is quite old in how we keep time on stuff. So a year is kind of a long time. People want something a little bit shorter, and so what's in a month? And so the first marker to demark time in the year was the moon. And that is, in fact, the root word of month, moon, month. That's why that's related. And there's a great shot of the Aztec calendar stone. And they used the moon, a lunar-based calendar, to subdivide and the cycles of the moon for their years. There's two main obstacles with using the moon to subdivide the year. The first is that the lunar month is not a constant. It varies. It varies between about 29 and 30 days. And this variance is due to using what is called the synodic period rather than the sidereal period. The synodic period is just what it looks like, right? Full moon to full moon. It's fairly easy to observe, but it's not terribly useful because it varies around a little bit between about 29 and 30 days. So your clock has a little bit of fluff in it if you want to use the synodic period, although it's very easy to observe. The real period, that's how I know it's sidereal. It's the real period. This is the time between identical alignments of, let's say, a star, the Earth, and some object. When all those align, that's the real period. This is the period that you would stick in Kepler's third law, but it's a lot harder to observe than simply full moon to full moon or something along those lines. So why is there a difference? Let's cover that a little bit. So I've got an alignment here. I've got the sun, I've got the moon, I've got the Earth, and I have a distant star. Okay, so I got 4 objects here. I've depicted, I'm just going to start everybody in a line. So this is my starting position. The Earth is going to go around the sun, the moon is going to go around the Earth, and let's take a look at the various alignments. So here I've got everything aligned. It's a full moon, and I have a moon-star alignment. So that's our starting position, and then we say go, and we let the clocks go. So the Earth goes around its orbit in the sun. The moon does its thing around, and by the time that you get to the same Earth-Moon-Star alignment, this is the real period. This is a sidereal period. It's the rotation period of the Earth. So this is the period that you would put in Kepler's third law. And for the moon, this is to 5 significant figures, 27.322 days. But the moon is not full, right? Because the moon is not directly opposite the sun. In order for the moon to get back to its position directly opposite the sun, you have to travel a little bit more to get back to the full moon position. And so the whole reason why there's a difference between the synodic period, full moon to full moon, and the real period, the sidereal period, is because the Earth is moving around in its orbit. And so by the time it does get back to the full moon, it's variable because the Earth's orbit is not a perfect circle. It goes a little bit of elliptical orbit. And so that day varies around a little bit depending on whether you're closer to the sun or farther to the sun. The second obstacle with using the moon as a time marker within the year is that it doesn't evenly divide into the number of days in the year, 365.2422. It's not an even division. So if you take 12 lunar months of the average full moon to full moon period, 29.5, it turns out to be 11 days too short. And if you go 13 lunar months, and it's 19 days too long. And so going back to the beginning here, the whole point is to keep the seasonal calendar, the time that the sun says, with our imposed calendar synchronized. And so if you adopt this lunar calendar to talk about time, then after a while, then the hottest time of the year is eventually going to be occurring in what you're calling the winter months. And so we have this synchronization. So many cultures who adopted a lunar calendar got around this conflict by inserting an extra 13th month every few years in order to keep the two calendars synchronized. Speaking of the Babylonians and the Sumerians, it was in the moon and time. It was common practice in Babylon about 4,000 years ago that for about a month, a whole month after a wedding, the bride's father would supply his new son-in-law with all the mead he could drink. And mead is a honey beer. And since the Babylonians did have a lunar calendar, this period was after the wedding was called the honey month, or what we call today the honeymoon. And so this is just another example of a term that has its origins in astronomy that you may not think about. That's been around for quite some time. And there's many other terms associated with the moon and keeping time. We have lunatic, a blue moon, a wet moon, a harvest moon, a red moon, a super moon, all kinds of terms associated with lunar as we go through. But I'm just very impressed with all the beer you can drink for a month. Yeah, that doesn't happen anymore. And time went on, and the Egyptians came into a dominant position. And the Egyptians gave up on using the moon to mark time within a year, and they took a bit more radical approach. They divided the year into 12 months. This is why we have 12 months, goes all the way back to the Egyptians, of 30 days each, for a total of 360 days. And even the Egyptians knew that that wasn't right. And so at the end of every year, they added 5 days for an approximation of 365 days. But even they knew that 365 days was not good enough. Remember, it's 365.2422. And so extra days were randomly inserted in order to keep the seasonal and the calendar years synchronized as you go through. So this lasted for a while until the Romans, and originally the Romans had a crazy messy calendar. There were only 10 months in the year, with March being the first month of the year, the Ides of March. And extra days were inserted at random by different parts of the Roman Empire in order to keep the seasonal and calendar years together. Some of these Roman names are still with us. The most obvious ones are September, October, November, December, for being the 7th, 8th, and 9th, and 10th months of the Roman calendar. If you speak any romantic language like Spanish or something like that, and you count to 10, it will sound like 7, 8, 9, and 10. And so although they are not the 7th, 8th, 9th, and 10th months in our calendar with our 12 months, nevertheless, the names still go back to the Roman 7, 8, 9, 10. And we'll get to the reason why they're not 7, 8, 9, 10 in a minute here. So this was just crazy. The empire was growing, and commerce was growing, and so we needed a better system. And so 1 year before his death, Julius Caesar instituted a new calendar. Now they were going to be like the Babylonians. There were going to be 12 almost equal months. March was still going to be the first, Ides of March, totaling 365 days. And now we're going to get organized on when we're going to add these extra days in order to keep the calendar synchronized. So it was every 4th year or leap year, there was going to be 1 extra day added at the end of the year. And this gave an average year of 365.25 days. Pretty good. It's not quite 365.2422, and we'll get to the implications of that soon. But it was pretty good, 365 and a quarter. And this is where we get leap years from. Every 4 years is leap years is from Julius Caesar. So Julius liked his new calendar so much that he decided to name one of these new months. Remember, there's now 12 months instead of 10 months. He decided to name one of the months after himself. And this is where we get July. July is for Julius Caesar. Money and power go together. And so one of Julius's benefactors at the time was the Juno family, a wealthy participant in the game. And so he decided to honor them, and that's where we get the name of the month, June. June for the Juno family, July for Julius. And now the pattern was set. Every ruler after Julius decided to name a month for himself. Fortunately, none of them stuck, except for his grandson, Augustus Caesar. And this is where we get August from, is for Augustus Caesar. So June, July, August from the Roman Empire and the Roman rulers, Juno family, Julius and Augustus Caesars. Now, as we talked about, 365.25 is a good approximation, but it's not perfect. It's about 11 minutes too long, or about 1 day in 130 days. Who's going to worry about that? Or about a week after 1,000 years. Who's really going to worry about that? Well, time marched on. 1,000 years did go by. And so by 1582, the seasonal and calendar years were about 10 days out of sync. And if you take a look closely at this calendar here, you notice something pretty strange. October 1, 2, 3, 4, 15. And so in order to get the calendars back in sync, a radical step was necessary. This was taken by Pope Gregory, who just chopped 10 days out of the calendar to get things back on track. Of course, this caused enormous social mayhem when he did this, because do I not get paid? What if my birthday was all October 6th? I don't get a birthday. Do I still have to pay taxes on the days? Just general chaos in economic and social lands from chopping 10 days out of the calendar. But nevertheless, it was done. And this is where we get a lot of the things we have today for the calendar from Pope Gregory. This is where January 1 was made the beginning of the year, away from the Roman March 1, because they were pagans, so to speak, and we can't have that. So he shifts the 0 point, right? He just shifts the 0 point from March 1 to January 1. Fine, no big deal. It's just the 0 point shift. He still keeps the Julius's system. Every 4 years, there's going to be an extra day added to February. That's all fine. So he hasn't done anything new. Now he does do something new. And he says that century years that are divisible by 400 are also leap years. So 1700, 1800, 1900 are not leap years because they're not evenly divisible by 400. But 1600, year 2000, are leap years because they're evenly divisible by 400. And so we just went through one of these 400s in the year Y2K, Y2000. The next one will be in the year 2400 when this is applied. And so this Gregorian system is pretty good. It's a lot closer to 365.2422. It's about 38 seconds short, or about 1 day in 2200 years. So we've been doing this game of keeping the clocks together for several thousand years. What are we going to do? Are we going to wait another 2200 years or another 10,000 years until the clocks are getting seriously out of sync and we need to chop days out of the calendar again? No. We don't do that anymore. So in the modern year, 1 second is added to the calendar clock at midnight, if it's necessary, on June 30th or December 1, whenever the difference between the seasonal year and the calendar year reaches 1 second. The rotation of the Earth is somewhat chaotic at sub-second levels, all kinds of reasons for that. And so it is not always the case that a second is added. Sometimes a second has been subtracted between June 30th or on June 30th or December 1. So if it's needed, those are the 2 dates when it is done. The calendar clock, what we call time, what we want to impose our system on the universe, is set up by a network of atomic clocks. That's how we keep time. That's how we define the seconds, is through atomic clocks. The seasonal clock, what the sun says, is all based on Earth's rotation, which again is a little chaotic at the sub-second level, and that is kept by the International Earth Rotation System, and their lovely bunker is shown there on the right, at Cement Brick House. Keeps track of the U.S. Naval Observatory of Earth's rotation. And so these are the two. These are the atomic clocks, keeping our calendar clock, and then tracking what Earth's rotation does, and we adjust as need be. And even this 1 second addition here and there is needed causes enormous disruption in the financial markets because trade goes on 24 hours a day. And so there's all kinds of proposals going on right now how to adjust this more smoothly, how that 1 second is added in. Because with billions of dollars moving every second, people get concerned when all of a sudden you chop out a second or you add a second. So even at the second level, we're still refining our ideas on how to best synchronize the calendar and the two calendars, the seasonal calendar. So why are there 7 days in a week? How come there's not 8 days in a week or 10 days in a week or 3 days in a week? Where'd that come from? Well, because there are only 7 objects that change their position on the celestial sphere: the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And so our names, and so each one of those was special. And so of those 7 objects that moved in the night sky, That's why there are 7 days in the week, because if you're moving in the night sky, you must be pretty special. And so you get your own day. And so our names for the 7 days of the week comes from the North Celtics. We have Sunday, that one's kind of obvious. Moon Day, Monday. Tuesday for Mars. Wooden Day for Mercury. Thor Day for Thursday. Freya, the only female in the group. Freya, Venus, the only female planet. Venus Day. And Saturn Day for Saturn. So that's where we get the names, days of the week. The days of the week are named after the planets, which some people get surprised about. And then finally, time zones. Where does time zones come from? Time zones were imparted by travel. Because before there were time zones, when you said the train was going to come at 2 o'clock, nobody exactly knew what 2 o'clock that was. Was that the 2 o'clock locally in San Antonio, Texas, for example, or was that 2 o'clock somewhere else at the station, or when it left? It was a huge mess. And so as transportation and particularly finance ramped up, there was a need to impose some order on time. And so it was actually trains that set up the time zones, first in the United States with the 4 zones. And then as travel began to spread across the world more globally, it was finally adopted by the forerunner to the United Nations in about 1920s or so, 1920s. Implementing the time zones. And you will notice, of course, and if you ever looked at time zones, they are not just strictly 24 lines running north-south to the globe. There's a bit of bending to local geopolitical realities. And so that's why the lines are not straight. And it's also where we set the international date line. Now, it's an arbitrary one, but this is where the date is going to change from one day to the next as we keep our clocks. And so this whole system of time zones, international date lines, all that comes from travel. And that's what I wanted to say about time through the millennia as we try and keep our desired clock and the clock with the Earth's rotation and the sun stay synchronized. Okay, cool.
Perfect timing.
Say again?
Perfect timing.
Ah, yes. Okay, where are we at? Screen share. Cancel screen share. Am I not screen sharing anymore? What do you see?
I see you.
Oh, no more. So the screen is gone?
Yep.
Okay, great. Okay, cool. So it's 11 o'clock. It's been an hour. That's been great. We will do one more of these in about 4 or 5 weeks. And this one was at 10 a.m. to get the morning people. Our next one will be at 10 p.m. Arizona time to pick up the night people and other people across the globe who are taking this course. So
remember to post questions so that we have stuff to talk about.
Absolutely. Remember to ask questions about the lab assignments. Happy to work out any of the quantitative stuff or the concept or qualitative stuff on the discussion board. And I want to thank you very much for joining today. And I look forward to interacting with you on the discussion boards. Thank you. Bye-bye.
Bye, guys.